People have been asking for more practice problems, which seems like a fair thing to do. The problem is that only shows you how to do one problem. So I'm going to do a practice problem, but I'm also going to talk a little bit on the side about the strategies that one should take when working on various kinds of problems so that you can apply these strategies to other problems, not just this particular one. And so let's just jump in. This is a problem from the Hughes-Hallett Applied Calculus text, and I'm going to write down a function, and woo-wee, it's a doozy. It goes like this, and what we're going to do is break this down. But first I have to write it all down. And as you can see, it's a lot of writing, and I'm still writing, and I'm writing, and I'm finally done. Except I didn't write it correctly. So let's write it correctly. And so we're going to go over this function. This is what you have to do if someone gives you a function. Is part of the problem is analyzing the function first to see what's going on. And so that's what we're going to do. And I have to also include some other stuff about one of the functions involved here. So here it is. Holy! So this is supposed to be a model of the number of hours of daylight in Paris, France on a given day of the year. So T is what day of the year it is. So January 1st is T is 1, January 2nd is T equals 2, so forth and so on. And what we have here is a kind of complicated function. And one of the things that you have when you have a complicated function, this is an active function that is modeling the observed daylight hours in Paris. It's actually not a very good model. It's okay. And so, so when you want to look at something like this, you need to understand what's going on with the function. And we get a sticking point here because this involves the cosine function, which we haven't talked about very much. So we're going to have to throw in some stuff about cosine. This is not unusual in a real problem where you have to bring in some other material that's not right on the page before, but that comes from somewhere out in your knowledge about the world or about mathematical representations of the world. So, oh, this has a function I'm not quite so familiar with. In a way, you don't have to be. There's one thing that you need to know about this function, which is its derivative, which we'll talk about. But the function is there. It's a function that describes what's going on. And so there's the situation. Okay, so ignoring the cosine for a second, which is one of the things that sometimes you have to do when you're working with mathematical formulas, is ignore part of it and come back to it. If we look at this complicated expression, remember, I'm going to scan this. You don't have to worry about copying this down. You can pause it and look. And what's happened here is that we've applied all of the tricks for modifying functions that were studied in pre-calculus and that we talked about before in the context of the basic functions. And so the tricks are horizontal translation, horizontal shrink, vertical translation, vertical shrink, and those have all been applied here to make this fit and make sense as far as what the hours of daylight in Paris really ought to look like. So to me, this looks like a plausible model, and let me tell you why. Okay, so first of all, with functions, you start at the inside out, and so I'm going to make a note here that the first thing on the inside is this t minus 172. That's the innermost part of the expression. And that's a translation. That moves things 172 units to the right. That's about half a year. So so that would make, that's a thing that would be plausible in the context of daylight hours. But this is just a translation. This has no effect on the derivative. It doesn't change the slope of the tangent when you translate a function. So, okay. The next thing we have here is a shrink or a stretch. And this is something that is very, very common in functions. We've seen it in other functions. The situation here with sine and cosine is that they repeat every 2 pi. And we want this to repeat every 365. So that's a simple unit change. And so this is a shrink or a stretch, depending. And this makes the period 365. So that's a very common trick with these periodic functions. So the natural period is 2 pi, and you divide by the desired period. If you wanted it to be 60, if you wanted like 60 hertz for electrical power, you'd divide by 60. Okay. Next, we have a stretch by a factor of 4. So that 4 out front takes the previous stuff inside the cosine, or whatever basic function that you've got there, and stretches it by a factor of 4, where the value used to be 1, now it's 4. And where the value used to be a half, now it's, minus a half, now it's minus 2. So that's just an ordinary stretch like you would do with any other function that you would bump into. Parabolas, or you've seen it with circles even. Those aren't functions, but you still have the same effects. So there's the stretch. And there's a name for this in the periodic world. This is called the amplitude. And last but not least, we have the plus 12. And so that is a translate up. So things that used to be at 0 are now at 12. The number of hours of daylight in the year centered around 12 instead of around 0. So that's just doing this to the graph. Start here, raise it up by 12. Okay. So what we have here is the cosine, which we're going to go into in a minute, and it has been translated and shrunk and stretched vertically and then translated vertically so that it fits the data. And so this is part of the art of making models, is this is now an active function that fits some observed data. And so the thing about an active function is that you can plug in anything, and nobody can calculate cosine. Well, some people can, but you don't want to hang out with them very much, especially at parties. But we have a friend that can calculate cosine. Google. It's showing you the wrong picture, though. Sorry. Google. So if you look at the search bar there, I have typed in this cosine function, at a particular value, and Google just tells me the value. So we'll need that value in a minute. So as far as calculating these things, we have machines that do this for us. So you just need to make sure the right thing is being calculated, but that's the situation. Okay, so let's get on with the cosine stuff. And so we'll make this kind of a sidebar. And so let me draw a quick picture of a triangle. Remember, there's no trig prerequisite for this course. So if I want to use these things, which you have to do, you can't do applications without cosine and sine, so we have to do them. And so I'm going to draw a triangle, a right triangle, with a couple of angles. Well, really only the right angle and an angle x, and the remaining angle has to be pi over 2 minus x. Some people say 90 degrees, but the calculus works out much better if you do your trig in radians, and so I'm not going to make a big deal out of it. We just assume if you're taking cosine of something, it's in radians. Okay, and I'm going to label the sides of this triangle. The hypotenuse is 1, and that makes the bottom side there, I'll show you in a second, cosine of x, and it makes the top vertical piece the sine of x. So those are the definitions of the function. So the sine is opposite over adjacent. So for this angle pi over 2 minus x, the sine of that angle is sine of pi over 2 minus x is cosine x. And so that's just one identity that you might need to bump into. And so cosine x is the sine of pi over 2 minus x. And again, if you need to calculate this, just Google it. Literally, Google it. Okay. And so when we want to take the derivative of cosine of x, this is a good review situation. We've got to use the chain rule because this over here is a composition. We've taken x and we've subtracted it from pi over 2. That's a function. It's a very simple function, but it's a function. And then, that's your cue to use the chain rule, we take the sine. And so the chain rule says if you have a composition of functions, the derivative is the product of their derivatives. And so in this case, what you get here is sine of pi over 2 minus, I'm sorry, cosine of pi over 2 minus x times minus 1. The minus 1 is the derivative of that inside function. The inside function is pi over 2 minus x. Its derivative is minus 1. And I'm sorry, I wrote sine. Cosine meant sine. Okay. So now if we look at what's going on here, this is just the sine, I'm sorry, the minus the sine of x. So this is probably one of the big useful derivative laws, that the derivative of cosine is the negative of the sine. Remember, the derivative of sine is cosine. Okay, let us return to Paris and see what the daylight hours are. And so we've got this function up here, which I'm going to rewrite. And so I'm going to rewrite it as quickly and accurately as possible because we're using a lot of electrons here on this video. There it is, the number of hours of daylight. Now the question, I said I was going to do an example, and I finally, after 11 minutes, I'm getting to the example. But we have to have these strategies to help us do things. So I am doing more than the example. So the example asks for values of d and d prime at 40 and 172. So 40 is the trickier one. But first we have to take the derivative of this thing. And this is a massive composition. So we have to be very, very careful. So let's take the derivative d prime of t, and it's the plus 172, that doesn't change the slope, that just moves it up and down. So when we take the derivative, we can ignore adding a constant. And so now we need 4 times the derivative of cosine times the derivative of what's inside. Oh my word, well, let's see what happens. Okay, well, 4 times the derivative of cosine, which is sine, times the derivative of what's inside. So being good at math, I do the parentheses first. I'm going to take the sine of whatever's in there. That's just going to be a copy and paste, and the derivative of whatever's in there. So we're taking the sine of 2 pi over 365 times t minus 172. And the derivative of that, it's just 2 pi over 365. So we've got 4 times 2 pi over 365 times the sine of this complicated thing, 2 pi over 365 times t minus 172. Okay, so there's the derivative. I've used the chain rule and done a little bit of simplification, but not much. I'd really rather let calculating machines calculate than me calculating. Okay, so let's now start plugging in some numbers. And they ask about on day 40, that's about February 9th, February 10th, somewhere in there. And so they ask for the value of d of 40 and for d prime of 40. So d of 40 is the number of hours of daylight, and d prime of 40 is the rate of change of the number of hours of daylight. And you've seen me enough that you know I don't care about d prime of 40. I might, but for my first pass, I just want to know positive or negative. And so there we go. So how am I going to get d of 40? Well, that's the example that I showed you here. And it's about 9.4. So I just typed that expression for d of 40 into the Google search line, and I got about 9.4. There's no need for this to be any more complicated than that. We're talking about a measurement that's made by people who have better things to do in the winter in Paris. So go have a cognac and enjoy your 9.4 hours of daylight. Okay. Now d prime of 40 is, I'm going to just do a little bit of preliminary work with this. So I've got the 4 times the fraction 2 pi over 365 times the sine of 2 pi over 365. Oh, is this going to be complicated or not? No. 40 minus 172 is minus 132. So the situation there is I've got sine of about 2, this is about, I'll show you what I'm doing here in a second. Oh, I forgot the minus in terms of the derivative, sorry. Sorry, let's fix all these minuses. Okay. This is approximately sine of 2 pi over 3. That is a very rough estimate, but there it is. And this is the minus sign. I forgot when I took the derivative. So put those minus signs in. They're here now on the notes. And sine of 2 pi over 3, I know, or you can Google it, this is positive. And so the overall derivative is negative. That's it. The number of hours of daylight is decreasing. And so that's what we need to work on. It's negative because of the sign out front. So if we look very quickly at 172, when t is 172 and we look at these formulas, then we're taking the cosine of 0 for the time of daylight. So cosine of 0 happens to be 1. You could Google that, or a lot of people remember it. D of 172 is 4 times 1 plus 12, which is 16, which is very close to actually being the number of hours of daylight in Paris on the 172nd day of the year. It's a very good model. And d prime of 172 is also interesting because it's 0. That's the solstice. When the sun stands still, the number of hours of daylight is not changing on that day because the derivative is 0. And then as you go on, you can get more changes in the derivative. But that's the point where you have the maximum number of hours of daylight. And so the derivative of the number of hours of daylight is 0 at a maximum. Okay, well, let us all enjoy our time in Paris. Remember, don't calculate these things. Google them. And the sine, the derivative of cosine is the negative of the sine. And that's really useful information.